Welcome everyone. So in the last class we have discussed about our isolated DC-DC converter, and it addresses the challenges which were associated with the non-isolated DC-DC converter, that was the absence of isolation between your input and output stage. Then we had limited voltage gain when we were talking about our non-isolated DC-DC converter. Then the solution which came into our mind was isolated DC-DC converter. The first solution which we have seen was our flyback converter. There it was the simplest isolated DC-DC converter, but what was the limitation of your flyback converter? There the leakage magnetizing inductance of the transformer was used as an buffer energy storage element. So what was the meaning of that? The magnetizing inductor of the transformer was storing the energy when the switch was on. When it was off, it was releasing the energy to the load. Now because of that, the power rating of our flyback converter was limited. So it was popular for low power applications, that is limited to 250 watts or 150 watts or so. Then to address these limitations of your flyback converter, we have come across this second solution, that is our forward converter. In this forward converter, if you see, we had 3 winding transformers. So the third winding was responsible for resetting your magnetizing flux, or the LM, magnetizing inductor energy, will be reset by using this tertiary or the third winding. So this is not the only solution of, or only way of realizing a forward converter. We can have different types of solutions. So this is the best efficient solution of forward converter, because we are recovering the energy which is stored in the LM when the switch is off. So we are discussing the operation of this converter. When the switch is on, we have observed that the dot will be positive because the source is directly connected to the dotted terminal. Then because of that, this dot will also be positive at that point of time. All three dots are now positive. As this dot is positive, clearly that D3 is reverse bias, so it will not conduct. This dot is positive, that is N2 dot is positive, so your D1 diode gets forward bias, whereas D2 diode gets reverse bias. Why? Because the moment D1 conducts, so this point will be connected to the dotted terminal of the transformer, so it will become positive. So now your D2 is reverse bias. So when the switch is closed, the energy flows from your source to your load by the transformer. Then what is the other phenomena which is occurring over here? On the primary side, if you see, the LM is also storing some energy because it is connected across the source. So your LM is charging, as well as the power is flowing from the primary to the secondary side, and LX is charging. Okay. So this is the scenario when my switch is in the closed condition. Now what will happen if my switch is open? So we know the behavior of the inductor, it will not allow instantaneous change in the current. So the moment I remove this gate pulse of the switch, or I try to turn it off, so the LM was seeing the current in this direction, so it will try to maintain the current. In turn, the current is leaving the dot on the primary side, so it will try to enter the dot on some other winding. So if you see, it can enter the dot through this winding, yes, because the diode can carry current in the direction of the arrow. Whereas D1, if it tries to flow through the secondary, will it be able to carry the current in this direction? No. So here D1 will be reverse bias. Now on the output stage, if you see, we have LX inductor. It was carrying current in this way when the switch was on. Now it will try to maintain that current. So how it will maintain that current? It will make this diode forward bias, and the current will flow through this loop. Okay. So when the switch is closed, here D1 gets off, the remaining two diodes, that is D2 and D3, they become forward bias, or they start conducting, and we will have two loops. Then we have seen the relation between the charging and discharging current of the output inductor. Okay. So here, as we have seen the different stages of operation, that is when the switch was closed and when the switch was open. So the delta Lx is the one which is responsible for energy storage over here, or it is used as buffer energy storage element. Now we are no longer using the LM, which was our transformer magnetizing inductance. We are not using that as the energy storing element. Now how to find out the relation between the input and output voltage? We will equate these two terms and make it equal to 0, because we are assuming steady state operation. So here inductor current should start from the same point, or average inductor current will be equal to 0, or the change in the inductor current will be equal to 0. So if I add them and equal to 0, I will find out that the voltage relation between your output and input voltage will be equal to Vsd into N2 by N1. Okay. So, if you see, this is the relation of our buck converter. Okay. So, V0 was given as Vs into D, and buck converter was called as a step down converter, because output voltage was always less than the input voltage, because the D is limited, or the duty ratio is limited between 0 to 1. So, for any value of duty ratio, the output voltage was always less. Will this forward converter be having that limitation, that its output voltage will always be less than the input voltage? The answer is no. Why? We have one more term, that is N2 by N1. So, I can just adjust my N2 by N1 during designing the transformer, so that I can obtain any desired output voltage as per the application requirement. Okay. So, now it is no longer an step down converter, but I can just adjust this turns ratio to get the desired output voltage. Okay. Now, the capacitor design. So, in this capacitor design, if you look at the output stage, it is something similar to the buck converter. Why? When the switch was on, this was the equivalent circuit. If you see, the source is connected to the inductor, and when the switch was off, the source was disconnected and it was circulating through the anti-parallel diode. So, this type of arrangement was present in the buck converter circuit. So, whichever was the capacitor sizing methodology used for buck converter, that can be directly used over here. So, this will be my formula to determine the capacitor size. Okay. So, if I am given with the percentage of ripple requirement, so I can just replace the delta V by V by the given percentage of ripple. So, based on that, I can find out the capacitor size. So, from where we have got this formula? From the analysis which was used to design the capacitor for a buck converter, because the output stage, this part of the circuit is same as that of an buck converter. Okay. Now, the other parameters of your forward converter. If you see, now we have introduced the current which will be flowing through your primary winding. Okay. So, what is this current, or why this current was flowing when the switch was off? At dt time, we have removed the gate pulse from the switch. Up to t0, why the current is flowing? It is flowing because of the energy stored inside our magnetizing inductor. Okay. So, we are assuming an point, arbitrary point t0 at the from the starting of my switching cycle. So, t0, this is the measurement duration, it is the duration for which Lm is in the conduction state. Okay. So, whether it is charging or discharging, when the switch was on it was charging, when the switch was off it was discharging. So, this t0 represents the total duration of conduction of Lm, okay, whenever there was finite current through Lm, whereas delta Tx is measured from the time instant when the pulse from the switch was removed or when it was going into the off state. This duration is called as delta Tx. Okay. So, now we will try to find out what will be the value of T0 and delta Tx in the next slide. So, these are the other currents. Okay. So, I2, when the secondary side current will be flowing, whenever the switch was on, the power was being transferred from the primary to the secondary side. So, secondary side will be seeing the current, which is nothing but the primary current reflected to the secondary side. Similarly, the tertiary current, what will be the tertiary current or the third winding current? So, it will be carrying only the Lm current, reflected Lm current, because it is flowing on the primary side as per our assumption. So, this will be reflected on the tertiary winding whenever the switch is open. So, this is the current which is flowing through this. Okay. So, why, if you see, it is marked positive. If you see, we are measuring this in this direction, the arrow is put in this direction. So, the current while the Lm is discharging is flowing in this way, which we have already seen. So, that is why it is marked as positive. Whereas, in this case, why I1 has been negative at the same instant of time? If you see, the measurement direction is on the downward side, whereas when the Lm was circulating the current, it flows in the upward direction. So, that is why we have got the negative current over here, but at the same point of time it has become positive as per our measurement direction. Now, Vx, what will be the Vx value? It will be the voltage across this inductor. Okay. So, what is the voltage across this diode? So, Vx is the voltage across this antiparallel diode, that is D2. Okay. So, when it will be carrying this voltage or it will be blocking the voltage, when the switch was on, we have seen that D2 was reverse bias. So, what will be the voltage across this one? As this diode is conducting, so this point will be connected over here, this point will be connected over here. So, the voltage Vx will be equal to the secondary side voltage or reflected primary voltage, because when the switch is on, the source was connected in parallel with the V1 terminals or the winding 1. So, it will be experiencing Vs voltage, V1 will be equal to Vs, that will be reflected on this. So, that will become equal to V2, which is being seen by Vx or the diode which is in the reverse bias condition. So, why this is important? This will give us the voltage rating of the diode, which will be placed as D2. Okay. So, now I have found out what will be the value of Vx when my switch is in the closed condition or when D2 was in reverse bias condition. When it is on, it will have 0 voltage. So, that is what is shown over here. Okay. So, now that will be helping me in finding out the suitable diode which can be used in the circuit. Now, ILM, what is happening to ILM? So, it starts from 0 at the start of the cycle till dt, it experience positive voltage, that is the source voltage is connected across it. So, it will be experiencing positive voltage and it gets discharged at t0 time. Okay. So, after this there is no current through LM because it has been completely discharged. So, what will happen to the circuit between this duration? If you see, this LM is no longer having any energy or the core of the transformer is perfectly reset or the flux lines are 0. So, there will be no current through circulating through this loop. Now, it will stop. So, there will be no current which will be flowing through the tertiary winding, only the state which will be in the conduction when the LM current becomes 0 is the output stage. Okay. So, now only this current will be flowing from T0 to T. So, this D2 will only be the device which will be carrying the current. Other two diodes will be having 0 current and the voltage across the transformer will become 0. Why? Because the switch has been opened and there is no driving force because LM has been completely discharged. So, after LM is completely discharged, only the output stage will be seeing the current. Now, delta IL max, this is the current through the inductor now which is responsible for our power transfer because it was charging and discharging. Now, we have transferred the role of power transfer from LM to LX by introducing few more components and changing the converter from flyback to forward. So, what advantages this brings in? It addresses the limitation which was associated with flyback because it was dependent on LM for the power transfer. So, its power handling capacity was limited, whereas that issue is addressed in this converter because LM is no longer handling the power transfer. I can design the LX value or the external inductor can be designed to satisfy our power transfer requirement, or the circuit can be designed for the required power as per the application. Then now we will calculate the value of T0. Okay. So, before calculating the value of T0, we will find out the value of delta Tx. What was delta Tx? The duration for which my LM inductor will conduct during the discharging mode. Okay. Or after the switch is turned off, it goes into the discharging mode, and this delta Tx represents the duration for which the inductor LM is in the discharging mode. Okay. So, now what was the voltage which was applied when the inductor was in the discharging mode? This loop, if you see in this loop, the current flows because it is making the diode D3 forward bias. So, this will be carrying the current. So, what will the voltage across V3 winding now? If I see clearly in this loop, there is nothing else. Okay. Source is directly connected across here winding 3 in this way. Now, why I say that the energy is recovered in this solution and it is the efficient way of representing your forward converter or designing your forward converter. If you see in this case, the current is entering the positive terminal of the supply. So, what is the meaning of that? The energy which was stored in LM is now being fed back to the source, or we are recovering the energy which was stored in the transformer core. Okay. So, in this case, what will the voltage across V3 winding? Clearly, when I apply KVL, I will see that it will be equal to minus of supply voltage. Why minus of supply voltage? If you see, this terminal has been marked as positive, but when I apply the KVL, I will see that it is connected to the negative terminal of the supply. Positive side is connected to the negative terminal. So, V3 will become equal to minus Vs. Now, that will be reflected onto the primary side. So, this is the multiplied with the corresponding turns ratio between the primary and the tertiary winding. So, now that will be equal to Lm Lm by dt. Okay. So, if I rearrange that and go for the simplification as we generally do, linearizing it and considering there is a small change in the value ILM value in small amount of time, that is delta Tx. Okay. So, what is delta Tx? We have already seen that is the duration for which the inductor is in the discharging mode. Okay. So, delta ILM was this was the current during the charging mode. So, whichever energy was stored in the LM during the charging mode will be released when it was in the discharging mode, then only it will get reset. Okay. So, if I make them equal and opposite and solve it, so I will see that delta Tx will be given by dt into n3 by n1. Now, it is dependent on two parameters, that is duty ratio and the turns ratio, okay, between the tertiary and your primary winding. So, this was my value of delta T0. So, now what will be T0 value? Delta Tx is given by this expression. So, what will be T0? T0 will be equal to the turn on time, the charging time plus the discharging time. So, T0 is the time for which LM will be in the conduction mode, whether charging or discharging. So, this is the charging time and this is the discharging time which we have determined. So, if I replace them and combine and try to solve it or simplify it, I will see that T0 will become equal to dt into 1 plus n3 by n1. Okay. So, the current must reach 0 before the start of next cycle. Okay. So, it is an optional requirement for us or it is a compulsory requirement. Why? Because well, if you remember the discussion when we have carried out for the flyback converter, we had two different modes of operation in that, CCM and DCM, continuous conduction mode and discontinuous conduction mode. So, when we said the flyback was operating in continuous conduction mode, when LM current was finite for the entire cycle, or it was at least positive, or it was just touching 0 at the end of the cycle. So, then we said that the flyback converter was operated in continuous conduction mode. So, the question is, can the LM current be continuous over here? The answer is no. Why? Now, if you see, if LM, suppose LM current is continuous. Okay. So, what is the meaning of that? Suppose it starts, we have started the converter and during the charging time it has created 10 flux lines in the core. Okay. Then during the discharge time, suppose there were 2 flux which were left out. Okay. So, the discharge was not sufficient or the T0 was trying to extend beyond the switching cycle. So, it has again experienced positive voltage. So, from the 2 it will start increasing to 12, assuming the core is linear for our simplified analysis. Okay. So, although the core is not linear, we are just for example we are considering that. In the next cycle what will happen? Now, the discharging voltage is the same. Why? The source voltage is connected across the tertiary winding, that what is reflected over here in every cycle, whereas the charging it is equal to Vs. Whenever the switch is on, Vs is applied across LM. So, charging and discharging voltages are fixed. Why? Once the circuit is designed, this turns ratio will not change. Okay. The only variable which is available with us is the duty ratio. So, now in the next cycle again it will experience the same amount of discharging. So, it will be left with 4 number of core lines. In the next cycle it will go to 14 and then it will reset to 6 and so on, assuming the core is linear for a time being. Okay. So, what is happening over here? If you see, the core was starting with 0 flux, then it is increased to 2, then it is increased to 6, then it is increased to 2, and so on. In the next cycle it will go to 8 and so on. So, 0 to 4. So, residual flux or the flux which is present inside the core is slowly increasing. Then after few cycles we will observe that the core will go into saturation and this converter will stop working. Okay. So, over here the continuous conduction of LM is not desirable. Why? Because it will lead to the transformer core saturation, and while introducing our transformer in DC to DC circuit, we have already said that we should make sure that the transformer never goes into saturation or else the circuit may be damaged. So, now this is our mandatory requirement over here, that is the core should be perfectly reset before the start of the next cycle, or the total conduction time of LM should be less than the switching time period, both charging and discharging. If I replace the value which we have just calculated and make it equal to less than T, then we will see that the duty ratio into 1 plus n3 by n1 should be less than 1. That is what will be the relation which we will be obtaining over here. Okay. So, now for time being, if I assume n3 equal to n1, okay. So, why we are assuming this n3 is equal to n1? So, while the construction for reducing your cost, generally the n1 and n3 are wound together. Okay. So, what is the meaning of that? On one, suppose we have this as my transformer core or one leg, simultaneously we will put two wires. Okay. That will be n1 and n3, or obviously the thickness will be different because they will be subjected to different currents, but they generally have an same turns ratio, okay, because they are generally wound together. Okay. So now let us assume that n3 is equal to n1. So what will be the value of our duty ratio? So it will be restricted to 0.5. Okay, why? This has become 1, so 1 plus 1 will be giving me 2. So duty ratio should be less than half or 0.5. Okay, so maximum duty ratio is limited to 0.5 when n3 is equal to n1, which is generally true. So my forward converter has faced one limitation because of this requirement that the core should be reset. So its duty ratio would be limited to 0.5. This is one of the demerit or drawback of our forward converter. Before going into the other drawbacks of our forward converters, we will see multi-output forward converter. Okay. So what is the meaning of multi-output? Or there are multiple output ports. If you see in this example, we have considered 3 output ports. Okay. So in these 3 output ports, if you see, we have only one switch, that is the primary side is common for us, and we have introduced multiple secondary sides or multiple windings on the output side of the converter. Okay. So what advantage it gives us? The advantage is the cost will be less. Why? We have 3 outputs, but the input side is common. So the number of components required to realize this circuit compared to the number of components which will be required when I design 3 independent forward converters will be, obviously here it will be the less compared to the 3 independent converters. Now for some merit we should get some limitation. So what will be the limitation of this solution? It will suffer from master slave issue. Okay, so what is the meaning of that? How many degrees of freedoms are available with me? So if you see, only the degree of freedom which is available with me is the duty ratio of the switch, because once the circuit is designed, this NA, NB, NC turns as well as N1 and N3, they will be fixed. Okay, so once the circuit is designed, we will not be able to change the inductor, capacitor or diode rating. Once it is designed, they are fixed. Only variable control by available to the control system is the duty ratio of the switch. If the duty ratio is changed, suppose I have an voltage requirement of 100 volts over here, and suddenly due to the load change, now I want 80 volts over here. Okay, so there was 20 volts drop in the required output voltage of this stage. So how I will adjust this drop in 20 volts? I will adjust the duty ratio, because all other parameters are fixed, that is turns ratios are fixed after the circuit has been designed. So I will change the duty ratio to reduce the voltage by 20% at the output terminal of port 1 or port A over here. Okay. So what will happen to port B simultaneously? If these two ports were operated at the rated condition, or the load which is requiring rated voltage is present over here, but the moment I adjust this duty ratio, they will also experience drop in their voltage. Okay. So what has happened? I am considering the port 1 or the port A as the master port over here, master port. So this master port, whenever there is some requirement of change in the voltage, that will automatically change the output voltage of the other two ports. Okay. So because of that, this solution, although it was cost effective, but it comes with an drawback or limitation, that one of the port will be able to regulate its voltage as per the requirement, the other two ports will be following it. Okay, so that's what the port which is denoted as master will be able to regulate the voltage, whereas the other two ports will be just following the required voltage of the master. Okay, so they do not have any independent controls which is available with them. Now the limitations of your forward converter. Okay, so what are the limitation of forward converter? If you see, this is your BH loop of the transformer. Okay, so this BH loop come across in the first year of your engineering, where this is the charging and discharging, or the flux is bidirectional, that is, it is both positive and negative. Okay, so if I see the flux lines which was created in this forward converter or your flyback converter, what was the LM current value? It was always positive. It was either charging or discharging, but it was never going in the reverse direction. So we were limiting the operation in the quadrant 1 only. Only one side of the core was being used, the other side of the core was not used, because we were not making the flux negative. Okay, so what is this other side? When the flux is negative, what is the meaning of that? If I mark the anti-clockwise direction of flux establishment as positive, so if it is negative, it means that the flux line should be flowing in the clockwise direction. Okay, so in the core. So The transformer core can handle two directions of flux, or it is perfectly bidirectional, but our converter was not allowing the flux to reverse because it was an unidirectional converter and the current was always positive. So that is why we say that the transformer is underutilized. Why? We are only using the positive side, the core volume will be higher for a given power rating. Okay, so compared to the solution where if we are able to use both the sides, the core volume will be less. So we say that the transformer is underutilized in our forward converter. Maximum duty ratio is limited to 0.5, that we have already discussed in details. That is, the core has to reset before the start of your net cycle if N3 is equal to N1 or the tertiary winding and the primary winding turns are equal, then my duty ratio will be limited to 0.5, which we have already discussed. Voltage rating of the switch, it will be greater than the source voltage. What will be the voltage across the switch? Again, in the turn of time, when the switch is in the off state, it will experience some voltage. That we have split into two parts. One, when the LM inductor is discharging. Once the second part is once the LM inductor is discharged. Okay, so this is the duration for which the LM is discharging. It is after the discharge of your LM, that is from 30 to T. Okay. So during this state, when the LM are discharging, what will the voltage which will be applied across our switch? If we go back to our analysis, okay, over here, okay, so the switch is off over here. What will be the voltage across this? Okay, so I have to apply KVL in this loop because the switch is present in the primary side. The moment I turn it off, what was the voltage over here? It was the reflected primary voltage from the tertiary side. Okay, now if I apply KVL, I will see that this source voltage plus this reflected source voltage from primary to the tertiary to the primary side will be coming in the loop. Okay, so both of them has to be blocked by the switch. So what will be the rating of the switch now? For this case, it will be equal to this Vs minus V1, whereas V1 was itself negative because we have already discussed this, because the positive side of the source was connected to the dotted terminal, undotted terminal of the transformer, and dotted terminal was connected to the negative side. So we have got negative Vs1. So when I replace it, I will see that Vs will be equal to 1 plus N1 by N3. Okay, so this is true when the LM is in the conduction state. Once the LM is discharged, we have already discussed that the current will only be restricted on the output side and all the other components will not carry any current. So when the other components are not carrying the current, so what will be the voltage across the switch when this current is missing? So there will be no reflected voltage over here, so I can assume it to be 0. Okay, so if I apply KVL, it is only the source voltage which has to be blocked by the switch. Okay, so for the switch, it will experience two different voltages based on whether my LM inductor is conducting or not. Okay, so when it is in the conduction state, it experiences Vs plus N1 by N3 voltage. When it is in the off state, it experiences only the source voltage. Now what will decide the switch rating? Obviously the highest voltage among these two, so that will define my switch rating. Or else if I design an switch which cannot withstand the highest voltage among these two, it will be damaged. Okay, so if I see, obviously out of these two, this term will be higher because it has some 1 plus something else. Okay, so if with the same assumption that N1 is equal to N3, if I replace that, I will see that it will be equal to 2 times of Vs. Okay, so the device rating or the voltage rating of the switch which will be used in a forward converter will be higher because it has to block 2 times the required source voltage. Okay, so the source voltage, if I consider that to be the battery bank, so it should be rated to 2 times of the battery bank voltage. Okay, so why it is limitation? As the voltage rating of your device increases, the cost of your device will be increasing. So if somehow I am able to reduce the voltage rating of the device, the converter cost will be reducing. So these are the three prominent limitations of forward converter, and it is also an unidirectional converter, that is the power will be flowing in one direction only. The reversal of the power or recovery of the power is not possible. Okay, so we have seen what is the importance of recovery of power in our EV applications. Okay, so the battery may be recharged by using the excess energy which is present inside the vehicle during the downward motion or downhill motion or during braking. Okay, so the to address the challenges of your forward converter, we have other options, that is full bridge brace DC to DC converter, push pull DC to DC converter. Those solutions we are not seeing over here because of the time limitation. We will go to the advanced solution, that is our dual active bridge converter. Okay. So, why it is called as dual active bridge? Okay. The dual active bridge, if you see, it has two bridges, one on the primary side, one on the secondary side, and they are constructed by using your active devices. Okay. So, what are their active devices? Fully controlled devices. Here we are considering the example of IGBTs. The working will remain the same even if I design the circuit by using your MOSFET. Okay. So, any fully controlled device will be making the operation similar, or the DAB operation is same if I realize it by using IGBT or MOSFET. Okay. So, how I will decide whether I have to go to IGBT or MOSFET? We have already discussed in the first few lectures. When the power rating is very high, we go for IGBTs. When the power rating is less, we go for MOSFET because it can operate at higher frequency and it will be having low switching loss. Okay. So, what is the advantage of increasing the frequency? The size of this transformer will be decreasing. Okay. So, based on my power rating, I will select whether to go with MOSFET or an IGBT, but the operation will be the same for both the types of realization, whether it is IGBT or MOSFET. Okay. So, how many devices are present over here? If I count 4 on the primary side, 4 on the secondary side, so it has 8 active switches. Okay, or 8 fully controlled switch. This inductor which is shown over here, it can be an external inductor or it can be the leakage inductance of the transformer. Okay. So, while discussing the transformer equivalent circuit, we have already seen what is a leakage inductance. Okay. So, I can design it appropriately so that the required inductor over here will be achieved from this leakage inductance. Okay. So, if the value is much higher, we generally go for connecting an external inductor without adjusting the transformer design. Okay. So, as for my application, I can connect an external inductor or I can adjust the leakage inductance of my transformer. Okay. So, here also we are neglecting the other component, other loss components of the transformer, that is the resistive drop of the coil as well as the core loss in the circuit for simplicity of our analysis. Okay. So, we are just connecting the leakage inductor or an external inductor. Okay. So, whether it is leakage inductor or external inductor, the operation will be the same which we are discussing now. The advantage is transformer is utilized in better way. When I go into the operation, we will see that the current will be bidirectional over here or the flux will be bidirectional. So, the core will be charging in one direction, then it will be reset, then it will go into the other direction. So, the transformer core volume will be reducing or transformer is better utilized in this case. Bidirectional power flow is possible. So, in the flyback and forward, we have seen that they are unidirectional converter. The power was not able to flow in the opposite direction, whereas in this case, this converter is perfectly bidirectional. That is, the power can flow from V1 to V2 or from V2 to V1 as per my requirement. If I have EV battery bank on one side and the DC bus on the other side, the power can flow from the battery bank to the DC bus, or from DC bus it can be recovered into the battery bank or it can be recharged. Okay. Now, let us see how this dual active bridge will be working. As we have directly jumped into the dual active bridge, we will go for some simplification so that the understanding of the circuit becomes easier for us. Okay. The first, what simplification we will do, we will consider that the secondary side bridge is absent. Okay. So, this is not a practical solution. We are just considering this assumption, that is the secondary side is short circuited, to see the behavior of this circuit. Okay. Just for our analysis, it is, there is no use of the circuit because there is no output terminals over here, it is short circuited. Okay. So, now this is my dot. Okay. So, we have seen what is the importance of dot. There is denote the instantaneous polarity of the winding. If one of the dot is positive, at that point of time the other dot will be positive. If current is entering one of the dot, it must leave through the other dot so that the power consumed by the transformer becomes 0. Okay, assuming the losses are 0. Now, we have considered the turns ratio to be 1:n, where n can be any number as for the application requirement. Okay. Now, in this circuit, we are assuming that we are providing this type of pulses. S1 and S4 are controlled in pair, that is, they are given the same pulse. The complementary pair is S2 and S3. Now, what is a complementary pair? If I can call two devices, that is S1 and S2, to be complementary. If one of them is on, at that same point of time the other one has to be off, and vice versa. Okay. So, if that condition is satisfied, then we say they are operating in complementary mode. Okay. So, here S1 is complementary to S2, S3 is complementary to S4. Okay. So, what is the advantage of this complementary operation? I can use a single gate driver. Okay. So, for IGBTs generally we get the gate drivers in pairs which will be driving one leg. If we have this complementary operation, that will be beneficial for us. Okay. Then with this assumptions, now let us see what happens to the circuit. Okay. So, if we give this type of pulse, what will be the operation of the circuit, assuming that we will have one more assumption, that is at the start of the cycle IL current is assumed to be finite and negative. Okay. So, that will be our symmetrical operation point. So, we will assume that it starts from negative and we will see what happens to the circuit when this type of pulse is given to it. Okay. So, if my inductor current is positive, okay, we will go for two stages of analysis, when the inductor current is positive and when the inductor current is negative. Okay. The first case, when the inductor current is positive, what is the meaning of that? It flows in the direction of our measurement. Okay. So, if the inductor current is positive, so it will flow in this way. Okay. So, if you see, the IGBT can carry current in the direction of arrow. So, this current is flowing through the arrow mark, or in the we where the IGBT can come in the conduction path. If IL is positive, then my IGBTs will be conducting. So, it will be flowing through the switches S1 and S4, and this will be the path. Now, the complementary case, if now at that point of time, if IL is negative, okay, so at any point if IL is negative, it means that it is flowing in this direction. If it flows in this direction, how it will complete the loop? It has to flow through the anti-parallel diodes. Okay. Why? The IGBT cannot carry current in the upward direction. It is an unidirectional current device, so we generally connect an anti-parallel diode to make it bidirectional. Okay. So, this current, when the IL is negative, the diodes D1 and D4 will be coming into the path. Okay. So, this is our simplified circuit where we have considered the secondary side to be short circuited. Okay. So, this is not the practical solution because there is no output port over here. Okay. So, we will stop at this point for this lecture. Okay. So, what we have seen in this lecture, we have first started with our forward converter. We have seen the limitations of that. Its duty ratio was limited to 0.5, the flux was unidirectional, it was an unidirectional converter, and the voltage rating of the device was higher. So, we have shifted into our converter, which is called a dual active bridge, which contains two active bridges, one on the primary side and one on the secondary side. We are now discussing the operation of this DAB by considering few simplified steps. Okay. So, we will continue from this point in the next lecture. Thank you.